We'll get started here shortly. Thanks for your patience. All right. Just as a reminder, this session is being recorded, and I will be sharing this recording in the announcements. It'll take me a couple of days to get it ready for you, get it captioned, and then I will post it in the announcement. So let me go ahead and turn my camera on here. Thank you for joining in, Savannah. I appreciate it. All right. So I'm going to go ahead and share my screen now. And I was working on updating some of the announcements while I was waiting for folks to join in. But I'll go ahead and I'll start with the announcements tonight. So I'm just clicking on a link there just to kind of show you some of the things that you have access to help with this week. I did want to remind everybody that I have to turn in an attendance report by Wednesday, if I'm not, no, Thursday. And so, you know, I think most of you have already gone out and done at least the week one assignments. If you didn't do week one and you have started something for this week, that'll be fine. It's fine as well. But the main idea is that you need to have something completed for this course in order to get marked as a show. That's the rules that the college has established. So I think, you know, like I said, most everybody has done so, but and I'm primarily speaking to those people who might not be here, who fall into that category. You want to make sure that you get something done between now and then, because if I turn you in as a no-show, they're going to drop you from the class. Okay. So also, I have some video recordings that deal with this week's material. And I'm going to talk about the project here in just a few moments, but there is also a project video that you can watch. So, you know, you might want to watch that in addition to what I'm going to be talking about tonight. And just know that it's there in the event you want to go back and refer to it. Don't forget, I put some items under extra resources. Okay, the extra resources, if you click on that, there's a folder dealing with every topic that we cover. And these are some extra notes. Sometimes I go out and take a look at them because they have some really cool examples. Like tonight, when I talk about unit conversions, I'm gonna go out and take a look at some of that. And it'll also kind of show you the kinds of things you have access to there. And finally, and you see, you'll be having access to extra videos from all the topics we cover. But also, I wanted to make you aware that, let me see where it went to. Yeah, videos from our class meetings. So like last week I recorded our session. There's a link to it, and then I'll just keep adding, right? There'll be a link to the recording for every one of our sessions, okay? So that at any point you can go and take a look at those. And then the extra videos are just like from some other class periods where I talked about some of the same topics, okay? So, you know, again, my goal is to try to make as many resources as possible available to you, okay? Any questions so far? No? Okay. We'll just keep chugging along. All right. So here I clicked on the weekly overviews. So the first overview that I'm going to take a look at deals with the nature of science. And you can see from the objectives, the kinds of things we want to focus on here. So, you know, we're kind of getting a little bit of background here, right? What are the ways of doing things in science? You know, why do we do this stuff anyway? How do we do this stuff? And then we'll take our first look at measurement, which is very important in the physical science that we're dealing with. And then once we get and have an introduction to measurement, then we'll go to the next overview and get a little bit deeper in looking at the way we do unit conversions, okay? So that's the goal for tonight. We want to get to the nature of science and measurement, okay? So just as a reminder, you have these activities on your plate for the week from this overview. You have a discussion that you have to complete that deals with the nature of science. So let me briefly click on that. So the way this works is, and you've done a discussion because you did the introduce yourself discussion, right? So you see there are a series of questions. You have to answer these questions. And then after you've answered the questions, you find two classmates, look at what they posted, and then you respond to them about what they posted in a way that shows that you're trying to engage with them regarding the actual information that they shared, you know. So you could look at things that you might look at how you explain something differently from the way that they did, or you might challenge them and say, hey, you know, I'm not quite sure that you're approaching this correctly. You know, we always want to be kind, right? When we respond to our classmates. I think somebody has an open mic. I can't hear you.
Hello, everyone.
Yes, mute yourself, please. Thank you. Right. Are you hearing me okay though, right, Savannah? Just thumbs up for me. Okay, great. I just want to make sure because I wasn't sure if you were trying to tell me you couldn't hear me. All right. So again, I was just sharing, you know, talking about the discussion that you have to do this week on the nature of science. That's due by Saturday. So you come out, answer the questions, and then you engage your classmates in a discussion about what you posted and what they posted, just as if you were in the classroom working in groups, right? So if you're in the classroom working in groups, you would have a discussion back and forth about answers to these questions. So you want to do the same thing in a discussion. It's not appropriate to just say, I like what you posted, or I agree with what you posted, or I got the same thing as you did, without giving a more in-depth and detailed explanation of why or how or what you think is right or wrong about what somebody posted, right? So you want to do that kind of thing, and you know, and engage. That's what I'm looking for. Okay. Any questions about the discussion that you're gonna do? Linda. That's my puppy barking. Sorry, y'all. I don't know why she's going crazy, but all right. So hold on just a moment. Sorry, she's barking because somebody just came to the door. I guess she's my guard dog. Okay. So let me go ahead and share the screen again. All right. So that takes care of the discussion that you have to do in this overview on the nature of science. I put a link here to the project. So I want to take a minute and talk about that as well. It's not that you're going to be completing the project. You have until almost the end of the course for that. But what I want to do is give you enough information so you can get started on it. Okay. So let me click here. Now, there are a couple of ways you can get to the project. Notice I just clicked on it from inside the weekly overviews. You can go to the weekly overviews, and there are links to the project information. See here, project, all the way at the bottom, project. So there, it's in the weekly overviews. You could click on the syllabus link and it's listed there, and a listing of assignments. You could click on assignments and activities on the left menu, and there's a link to the project that way. Okay, so there's multiple ways you can get to the project information is what I'm trying to show you. So you know, access it whichever way you feel comfortable. I typically go to the left menu because I'm so acclimated to using the left menu for everything. Okay. So everybody in the class has to do a project. It's worth 100 points. And you can see that there are some skills that you're trying to build in doing this project, using the library and library databases, using online tools, properly citing information, and preparing. When it says here a presentation, that it doesn't mean that you're going to do a presentation. When they say prepare a presentation, they mean a written paper, a written report. Okay. And so we'll get to a lot of these other things here later, but what I want to do is I want to take a look at the project details to get you started. So you have some deadlines mentioned here. So the article that you're going to be using for the project has to be approved. And there is a listing telling you that the deadline for that approval is the 22nd of October. And then the actual full project is due on the 26th of November, okay? So that's a reminder there. If you click on project details, you have access to pretty much the same information here, explaining to you why we do the project. Again, to get familiar with library resources, and to, basically to improve your information literacy type skills, right? One of the things we focus on here is using the APA format in limited capacity, because I want you to be at least familiar with APA, the American Psychological Association format, because that's used in all scientific writings. So in an English class, you might be using MLA style, but we don't use MLA in science, we use APA. And so you're gonna use some aspects of APA format during the course of doing this project, okay? And so, just move this up out of the way. So it says here the directions, okay? And that's what I wanna do, is I wanna give you enough information to get you started, okay? And then give you a chance to ask questions about the information that I'm sharing on how you get started. So you're gonna use a peer-reviewed research journal article. A peer-reviewed research journal article. Peer-reviewed means that people who have the knowledge, or the experts, get to scrutinize or review a research article that another scientist publishes in a research journal, okay? So that's your task, is to read and summarize one of these peer-reviewed research journal articles, and in your own words. So you're going to be reading it and summarizing it in your own words, okay? And you also have to clearly tell me how the article relates to what you have studied in lecture or lab, if you're in both. And if you are in both, you have to do 2 different projects, okay? So you can't do one project for both classes. You can't use the same article projects on 2 different articles, all right? So I like to tell students, when I explain what this peer-reviewed research journal article is, it's like a fancy lab report. For those of you in my lab class, you'll be doing lab reports on a regular basis. And you'll follow a certain template, which you'll see after tonight's class closely resembles the scientific method. A lot of the steps and items included in a lab report come directly from the scientific method. And so you're going to be reading one of these fancy lab reports written by a research scientist that's published in a research journal, so that all the peers and people in the academic and scientific community can have access to it, can read and scrutinize it. So you're going to tell me, so you're going to find one of these articles first, and then you're going to read it and tell me what it's all about in your own words. And you're going to connect it to the classes that you're in. If you're only in lecture, you only have to do 1. If you're only in lab, you have to, well, if you're only in lab, you're not here. But again, the most important thing is, if you're in both, you're going to have to do 2 of those, okay? So what do these articles have to be about? Well, they can relate to mechanics, which is motion in the physics world. Mechanics refers to motion, energy, waves, or thermodynamics. In astronomy, also, your article can also relate to astronomy. So let me add that there, because that's important. Not sure why that's not showing up on this one, but yeah. There, okay? So one of those 5 categories. So you're gonna find this research article that relates to one of those 5 categories. Well, how are you going to find them? Well, I mentioned library resources, right? The college has what we call electronic databases or e-databases. And you can use those e-databases at no cost. And you're going to use them to find one of these peer-reviewed articles, okay? So on the left menu again, there's a link to RPCC's library. So if you click that, it opens up in a new tab. And you see here, see a list of online resources. So if you click there, it's taking a moment. Hopefully that doesn't, yeah, there we go. Okay. And so you see here, there's a listing of databases. Okay. Now, for example, you know, I mean, I guess you could, but you know, if I were looking for a science article, I probably wouldn't be looking into the art and architecture database, right? Academic Search Complete. There's a definitely one that directly relates to science. You can see they're in alphabetical order. So there's probably get down to science, way down here somewhere. Science and Technology Collection. Those, so you know, the databases that that relate to the topic areas that you're allowed to utilize, right? Now, once you get into those databases, then you'll need to know how to search, okay? And there's a link right there that tells you how to access library resources, how to use them. So you need to follow that information in order to successfully deal with this project, okay? So let me close that window, okay? So that's how you access the library databases. And then let me go back, okay? Now, also, you see here, I put a note of caution to you, okay? You might find acceptable articles or scholarly e-journals that are online. So like if you went and did a Google search, you'll most likely find lots of articles, especially with those 5 categories. But many times when you find these scholarly articles by a Google search or Bing or whatever, you have to buy them. And one of my goals is to discourage you and tell you not to purchase those articles. Use the databases, the college's databases, because it's free. All right, to get these articles online out of you know, through a Google search, you have to pay for access to these scholarly journals. These are scholarly databases. The college has already taken care of the subscription fees for you. And so you can use the databases through the college's library website at no cost. Okay. If you don't want to use the college's e-databases, I've given you access to a free database. It's called Hindawi. Hindawi is an open access repository, meaning open meaning it's free. I mean, I could describe it other ways, but the best way to describe it for you is that it's free. And so when you click on the Hindawi link here, you're going to come to this website, and then you can see the little search glass there. You can come and start to type in what you're interested in. And I just type that, for example. And you see there are 8,364 articles that deal with medicine. So what I would have to do then is I would scroll through and say, oh, let me look at some of these articles I'm interested in alternative medicine. Oh, there's an article on alternative medicine. Let me see what else they have on. Okay, so I use the initial search and they have even more on that to kind of hone in on, you know, specifically what I'm interested in. And then I could look at those and say, okay, well, I'm interested in alternative medicine that deals with cancer. Okay, so let's see if I search. You see, so what I have to do is, oh, maybe, oh, they're 10,000 plus. So, yeah, so see, they got a lot of articles, right? So I'd have to know something about specifically what I'm looking for to kind of refine my search, okay? So you see here, I could tell it the article type, clinical studies, okay? And then, you know, refine my search that way. I could tell it from, so I could say from 21 to 22 and search and see, I'm still getting a whole bunch of them, right? So so basically what you would have to do is once you start getting a bunch of articles, you have to decide how to refine that search, okay? So, you know, maybe, let's see if I could make it select article type. Maybe I take off clinical study and just do conference paper. See, so yeah, you can see from this, there's like oodles and oodles of articles in this um, repository, and they're all free. Okay, so yes, you're gonna have, you know, you're gonna have to search and then refine your search until you get down to something that you're really interested in. Maybe you're interested in, you know, something about thermodynamics, but you don't know exactly what. So you can go out there and put that title in, search for it and see what all they have on that, and then start to refine your search to find the article that you're interested in that particular category. The other thing that'll help you is that your article has to be at least 15 pages long. Please pay attention. It says your article, not your summary. Okay, so the article is what you're going to read. The summary is what you're going to write. The article has to be at least 15 pages long, not including the references. So when you're counting pages, don't count the references. So I always tell students, if the references start before page 16, it's too short. Okay, so you're looking for a peer-reviewed research article, which is like a fancy lab report. You can use the college's electronic databases. You can use this Hindawi website, or if you want to use an app, say on your phone, then you can go to the Play Store or the iTunes Store and look for this RXiv. You see that RXiv. And when you search for that RXiv, you'll see a logo that looks similar to this. That's how you know you found the app, and you can utilize that app to also search for research articles, okay? And so you have between now and the 22nd of October, 11:59 p.m. to get an article approved, not to find an article, to have an article fully approved, because you have to get your article approved before you begin reading and summarizing, okay? So you go out, you find an article, you want to see if it's acceptable, you email me the full article, I'll look it over and tell you if you can use it or why not, okay? And you must get an article approved by that deadline, or you're going to lose 20 points on the project score, okay? And we'll talk about any other potential consequences. But for now, your goal should be finding an article and getting one approved. And you may be wondering, why am I telling you in August about something that's due way at the end of October? Because it is a process to find an article, okay? It does take some effort to find an article, all right? So let me just stop the share and I'll do a quick, okay? And so what I want to do now is just open up the floor and see if there are any questions. I see one here in the chat from Savannah. Yes, they are hard to read and understand. Absolutely. And that is another reason why you want to get started early. And especially if you have lecture and lab and you have to do 2 of them, you definitely want to get started with the finding and get that off your plate so you can have the time to read, you know, and digest. Okay. Right now, let's focus the energy on finding. Any other questions? Feel free to just unmute and ask your question. I can't hear you. If Savannah, if you're asking me a question, I can't hear you. No audio. Yeah, just type it in the chat. I'll be happy to answer it. Michael or Damien, if you have questions, please unmute. Feel free to ask your question. Oh, okay. Yeah, they are. They do take quite a bit to read and digest them. And we'll talk a little bit, you know, maybe in a couple of classes, we'll talk about where you're at in your search life. Have you found something? You know, have you gotten it approved? And then we'll talk about some strategies on how you make heads or tails of them. Okay. Okay. Thank you, Michael. Yeah, I appreciate that. All right. So what we're going to do now is go ahead and get back into tonight's material. So that's pretty much what I wanted to share on the project, just enough to get you started. So now we're going to go in and look at this weekly overview and jump into this nature of science stuff. And so I was explaining before a few of you came in that the whole goal for tonight is to acclimate you to some of the tools that we use in science, the scientific method, measurement, the metric system, how we do unit conversions, and so that you'll have those tools available to you throughout the course. Okay. So when you get into the overview, of course, the objectives that I just covered in a kind of short fashion, the activities, I talked about the project, I talked about this discussion that's due by Saturday. And then these are all tools that you can use to help you through the material. There's notes, there's videos, there's sample problems, depending upon what tools you need to tackle that material. My suggestion to you is to go through these items, and at any point, if something's not clear to you, that is the time to reach out to me, okay? And ask any questions that you might be having, okay? Now, I will say this to you. Typically, I cover the supplemental notes, okay? And those are I always tell students, those are my lecture notes. The other notes and videos are your notes to use independently. The supplementals are my notes on the topic, okay? And then I also showed that if you go into the announcements, there are some extra notes, extra resources, okay? And if you click on that, you'll see that there's a folder dealing with each topic. And actually, for tonight, I'm going to refer to the extra notes a few times because I like some of the examples that they've worked. Okay, a lot of times I'll go pull the extra notes because I like the examples, and the examples are indicative of the kinds of things that I want you to be able to do. Okay, so what I'm going to do now is I'm going to go into the supplemental notes on the nature of science, the supplemental notes on measurement, and then we'll have you know, a Q&A time period, so you can ask me any questions. In fact, anywhere along the way, if you have questions, don't hesitate. Ask your questions, and then we'll get into the measurement dealing with unit conversions. Okay, so let's go ahead and get into these nature of science notes. I can't see if everybody's following along, but if somebody will just write in the chat for me, if you can see the screen where I opened up this note packet, just type yes. Thank you, appreciate it. Okay, got it. I always like to ask because sometimes I have to stop the share and restart it to make things visible, okay? So I always like to kind of, especially, you know, the first time around we're tackling some physical science, give students some tips on how to study this, not just this module, but how to approach this material in general, okay? And so, of course, you know, it's important that you're keeping up with things. It's important that, you know, any words or terminology that that is unfamiliar or unclear, you need to either look it up or be asking. I try to explain things as thoroughly as possible, but if something's not gelling, please don't hesitate to ask me. You're following along with me in the notes that I'm covering. You're reading and reviewing the textbook and the resources that I provided. Of course, you ask as many questions as you need to, either in here or during office hours, if you know, if need be. I always tell students my office hours are open and available. And if that's not working, let's make a time where we can get your question answered. You're doing discussions. The idea of the discussions is for you to interact with your classmates, to become a support structure to each other as you work through this material. And review review the notes, review the materials, and then all assignments and assessments, right? So in order to be successful in this course, I hope you can see from that in a nutshell that you have to put forth the effort, okay? I tell students you won't learn this stuff through osmosis. There's no way without engaging with the material for you to be successful at learning it, okay? So in this packet, there's some key things that we want to do, and that is look at the scientific method. And then we want to look at the connection between science and technology. Now, that's not all we're going to do, but that's the primary focus of this packet, okay? All right. So, one of the bedrock ideas of science is that, we believe that nature it has an underlying order and simplicity to it, right? Yes, I would agree that, some of the ways we describe things and some of the math we use in science, especially physics, is it is complicated, but you know, that's our way of explaining the order and simplicity that nature, you know, that underlies nature, right? And so, you know, and we approach it with that mindset because that is what has fueled and allowed us the curiosity and capability of revealing and describing this order, right? I told folks, look, science is not the only way that we can explain the things that are happening in nature. You know, roses are red, violets are blue, right? Hey, I just described something, right? But that's not necessarily what we call science. So science is the set of theories and laws that help us to understand the way that nature behaves. The body of knowledge that we have amassed over the course of human history that help us to understand the way that nature works. And we can package that knowledge in the form of theories and laws, okay? And so, you know, that means we have to understand what do we mean by theory and what do we mean by law, and we'll take a look at that. But the idea is that, you know, science is a way that helps us to understand nature. And there are many different disciplines or fields in science, you know, astronomy, chemistry, biology, geology, physics. And so you're in this class to help to get an understanding of what we know about nature from a physics perspective. We do some a little bit of astronomy here and there, yes, absolutely. But our primary focus is physics, but not physics from that high level math or complicated math perspective, from a foundational conceptual perspective with some simple math type explanations or equations to help us understand relationships between properties that we come across in science, okay? And, you know, physics is one of those fundamental science that kind of is at the, you know, at the core or at the foundation of all the other sciences. In other words, the other sciences are built out of our understanding, fundamental understanding of nature, which is what physics tackles, okay? So physics has to deal with energy, matter, space, and time, and all those interactions. And we're looking at it from a fundamental perspective. I always say, you know, physicists want to know everything about everything at a fundamental level, okay? And notice what they say, that can be measured and tested. That is what distinguishes science from other things. This notion that we're measuring and testing. Physical science is built on measurement, and those laws and theories that we use to package our knowledge about how nature behaves have come about through measurement and testing, okay? And we like to think that, you know, it's this kind of a self-correcting process, in that we may get it wrong for a time period, but eventually somebody is going to come along and help us to get it right, okay? And so, you know, because physics is this fundamental science, things that are germane to other branches of science have to, you know, fit well and incorporate the fundamental laws and rules that we've uncovered in physics, okay? And so, you know, we also, you know, the benefit beyond just knowing how nature behaves, is that we can apply that knowledge, right? So physics is not just concerned with knowledge for knowledge's sake, but we also want to take that and use it to help, we like to think, to help our society in a productive way, right? And so, folk who are like engineers or applied physicists or, applied scientists in other fields, they utilize the fundamental knowledge that we've gained in physics to find ways to use that knowledge, hopefully to improve, our human and, our condition, right? Make things easier and better for us, okay? But you see here, for example, they give even sciences like architecture rely heavily upon the laws of physics, because the laws of physics explain how forces work that are essential if they're going to build buildings that, are structurally sound, and things like heating and cooling and lighting. All of the fundamental knowledge that physics has, amassed helps with though in those types of applications, okay? And so, you can think of a lot of different applications of the knowledge that we have, put together in physics. They give example, from of a microwave oven, right? You think about, the knowledge that has to be available to build something that we take for granted every day now, like a microwave oven, right? I always like to use, kind of explore the connection between science and technology. My favorite example is looking at the telescope, right? Because, you think about the telescope back in the 1500s, fairly crude telescope, gave us lots of knowledge about, our environment, our surrounding planets, moons, that kind of thing, right? But as we learned more, we were able to build better telescopes. And now those better telescopes are helping us to learn more about our actual universe, right? So they kind of this knowledge and applied knowledge, or you can think of it as theory and technology, kind of work hand in hand. The more we know, the better technology we build, the better technology we get, the more we learn. So they work hand in hand, okay? Okay. So they I like this this idea of science is job, goal is to describe things that, as it is, not from this imaginary perspective, right? We might, our imagination might be helpful in helping us to understand what actually is, and we might have an imagination about how things might be, but science focuses on what is, okay? And the goal is to improve upon our understanding of what is, these natural phenomena, the way nature works, right? And so one of the keys to our ability to do that, is our curiosity, for sure, as human beings, but at a basic level is the idea of observation, right? We have to engage in observation in order to fuel, that whole development of knowledge, right? So scientists make observations, and then they can start to formulate a set of, formulate a process for figuring out the rules and laws and theories that that phenomena that they're observing follows. Okay, so you think about, for example, way back in human history, just observing the motion of the sun, and then figuring out and coming up with a body of knowledge to explain the motion of the sun, and then taking it from the body of knowledge that explains the motion of the sun to having tools that help us deal with that better, things like clocks or sundials or whatever it might be, right? Based on our understanding, right? Or using that understanding to determine when it's best to migrate to another part of the planet where there's more food readily available, or to know when is the best time to plant seeds to grow food, right? So you can see that part of, our curiosity and this whole observation and then amassing knowledge, yes, definitely helps us to understand the way that nature behaves. But at a fundamental level, a lot of it is our understanding is geared to what? Survival, right? The more we understand that way that nature and things around us behave, the more we increase our chances of survival. And you don't have to think too far in this state to understand the importance of that. For example, with hurricanes, you think about for the many years in human history and human existence that, that whole science of that whole capability of understanding and predicting storms just really didn't exist, right? I mean, there were some clues that people could follow, but a lot of times, people dealt with a lot of death and destruction because they couldn't accurately predict where storms were going to hit and when they were going to hit, how strong they were going to be, and so people just weren't able to get out of harm's way, right? But now, while we still do have some really strong and catastrophic storms that do a lot of damage, there are the loss of life outcomes, I would like to think, are better because people can get out of the way, or hopefully they can get out of the way, right? But the whole idea is to have a way of giving that information so that people can make life and death choices or decide how to deal with their properties and survivability, right? So scientific models, theories, and laws. So this idea of scientific modeling, it means that we're going to take this complex phenomena or system and try to simplify it, okay? And they give an example here of electrons orbiting the nucleus of an atom and imagining that they travel in planetary-like orbits. Now, actually, the motion is quite a bit more complicated than that, but that's a simplified model. In this class, when we talk about projectile motion, for example, we'll approach it from a perspective of no air resistance, because that's a simplified representation, a simplified way to model that type of motion. When in reality, you're going to have air resistance, and that can make things a bit more complicated. But from our perspective, we're going to approach it in a simplified fashion. And even scientists who are actually doing research and work, they try to find ways to simplify whatever phenomena they're investigating. Okay. A theory. So this theory is an explanation for the patterns that is supported by scientific evidence and verified multiple times through reproducible experiments. Now, I read that directly because I wanted to really emphasize the fact that a theory is not just us guessing without any backing, right? I would tell people, if you're guessing without any credible evidence, that's an opinion, right? And a theory is not an opinion. It's not just a thought about how something works. It's an explanation based on many different experiments, by many different scientists in from many different disciplines. Okay, so you see, it's an explanation for patterns. That's key too. Patterns with an S, multiple patterns that help to explain the phenomena. And it's been, that explanation is supported by scientific evidence that comes through experimentation. Okay, a lot of people think that a theory is just us guessing without really having any reason for thinking that, and that's absolutely untrue. Okay, a scientific law, on the other hand, focuses on a particular pattern. Okay, and it is also supported by scientific evidence through reproducible experiments. That scientific law can often be expressed using a single equation, you see, whereas a theory is much broader because you have more than one pattern. A scientific law is narrower in its focus, and so you can typically utilize a single equation. Okay, like F equals ma that deals with force, for example. Okay, now, and they say that to you here. Generally speaking, a law just describes a single action, whereas a theory explains a group of related phenomena. So the theory of relativity or the Big Bang theory, whereas a law, for example, Newton's laws of motion, right? So we got, we're more singular in our focus, okay? Now, something else that you need to understand that's very, very critical, because this is where a lot of students fall apart here, is that they think these things, these theories and laws are set in stone. They're not going to change. And that is absolutely incorrect. Because if we get more credible evidence and explanations of any phenomena, we have to own up to it and change what we understand. Okay, so yes, theories and laws have been verified multiple times through reproducible experiments, but if we get better explanations, we must abandon our current understanding and accept the better explanation. I mentioned the idea of science being this kind of self-correcting process, because if somebody comes along with a more correct and better explanation through evidence, we must update our knowledge. Okay, so they are not set in stone. They can absolutely change. The scientific method. Okay, so a lot of the knowledge that we've collected, or the knowledge that we have about our environment, about nature, has been produced through following this process known as the scientific method. The scientific method is a problem-solving process. That's what it is. The scientific method is a problem-solving process that works best for science, because there are problem-solving processes that work for other disciplines, right? But the scientific method is the problem-solving process that we follow to help us uncover new knowledge or find ways to apply that knowledge. Okay, is it the only way of solving problems? No. Guess and check, for example, or Eureka, we were looking for one thing, we figured out something else. Voila. There are things that we know about nature that we figured out just by accident, and that happens. But more times than not, scientists are methodical in their approach to uncovering knowledge or finding ways to apply that knowledge. Okay, and so They tell you here that the scientific method typically begins with an observation, which leads to many times a question. And then the scientist next goes out and does some research. So you might observe a phenomena. You might wonder, how does that work? And then go look and see, has somebody already explained how this works? Why? Because we're not trying to reinvent the wheel, right? If somebody's already figured out the answer to that question, or there's lots of knowledge related to that general question, we want to have that available. So you go and research the topic and then come up with a hypothesis. See, a lot of people think that a scientist forms a hypothesis and then goes out to do the observation and the research. It's exactly the opposite. The hypothesis that we follow or form comes out of the observation, the questioning, and the research. Okay. And so after the scientist has formed a hypothesis, then they have to have a way to test that hypothesis. And that is where the experimenting comes in. So an experiment is an organized procedure for testing the hypothesis. Now notice, there are many things, beautiful things that we want to know about, but they're not testable. And so they're not science. Science relegates itself to those things, those hypotheses that are actually testable. Okay. And so through that test, the scientist either confirms the hypothesis, modifies it to conform to some new information or evidence, or discards it altogether and, comes up with a new hypothesis and repeats the process. This is the idea is not to do one, experiment and quit, right? We're currently in the stage of refining our understanding. So here I have listed for you some basic steps in the scientific method, right? Now, you might look at some other sources. They might break these down a little bit differently, especially the experiment. Sometimes they'll go into a little bit more detail. They might say, collect data, perform an analysis, draw results, conclusions. But the basic idea of the scientific method are captured here. And you can feel free to use these steps when you're doing homework or any other type of assignment. If you find steps in another source that you feel help you break it down in a much clearer fashion, feel free. Okay. So I put in the notes here, I like to call my crazy example of using the scientific method. Okay. And you'll see why in just a moment. And I did this on purpose because you have in your problem set number 1 to also use these steps. And I wanted to give you, an example of how the steps work. So we'll take a look at this and then we'll pause just for a moment to address any questions you might be having, and then we'll move forward. Okay. So it says here, the question, when the Titanic sank, what happened to the water level on shore? So, just imagine somebody's watching the movie Titanic and, the guy's on the thing going, I'm the king of the world. And somebody's like, hey, when that thing sank, what happened to the water? Somebody wants to know. So they go out and research, right? They go out and research. They read and synthesize all information that's available on the sinking of the Titanic. How big was the boat? How cold was the water? How big was the iceberg? How many people on board? All the information relevant to the sinking of the Titanic. And then based on all that reading and synthesizing, all that research, they form a hypothesis. Okay. Now, I don't know which one of these 3 they're going to pick, because That depends on the research that they did, right? But I suspect it'll be one of the three. The water level went up, down, or stayed the same. Depending upon the research, that's the hypothesis that they're going to test. Okay, one of them. Pick, whichever one the research guides them to. And it could be that somebody else already did research on the water level, and they determined that the water level stayed the same, and this person wants to go back and verify. Is that really the case? Because from what I'm synthesizing here, I'm not quite sure I agree with that. Maybe there's something about the way they did this experiment that I'm not quite sure they're right. So I'm going to go back and repeat to see if that's in fact what happens. Okay, so when we say research, we're looking at other experiments that people have performed as well. All right, and so they're going to do the experiment to test their hypothesis, and the question then becomes how. Because obviously we can't go back and resink the Titanic, right? And so the experiment that you perform is dictated by the resources and feasibility of the study. If you have unlimited resources, you can build you a boat that, is a replica of the Titanic. You can measure the temperature in the North Atlantic every day, every 15 minutes. And when the temperature seems just right, you can launch the boat. And I don't know if you get any people to go on that boat, but you get the idea, right? The amount of the resources that you have available will influence the type of experiment that you do. Okay. So, you have to be aware of that. And then there are just some experiments that no amount of resources will allow you to do that experiment. It's just not feasible. Okay. So once you do the experiment, you have data, you're going to analyze the data, right? And then you're going to draw conclusions. Was your hypothesis correct? If so, why? Is further testing necessary because your hypothesis was incorrect? And then you have to decide, okay, hey, what went wrong here? If further testing is necessary, what went wrong? What do I need to do differently? Or what's next? Maybe this was a great first step, but there's some future experiments that we need to do that will help solidify what we understand. Okay. Right. So I'm going to stop the share here and ask, what questions do you have of me at this point in terms of anything that I've covered? You said here, can a theory ever become a law? That's a great question, Savannah. By nature, because a theory involves many different patterns. Okay, so you're not just dealing with a single phenomena, right? So because they approach knowledge from a different perspective, right? So maybe some portion of a theory might become a law, or there might be some laws that when utilized together with our understanding form a theory. But because of the broad nature of a theory, because it's tackling this phenomena from many different angles, there's that typically is not going to become a law. Okay, so like the Big Bang theory is not going to all of a sudden become the Big Bang law. Okay, all right. Anybody else, please feel free. All right, so let me go ahead and share the screen again, and let's keep moving forward. And then the rest of this packet talks about the historical roots of physics. they try to to mention some of the key players, especially as it relates to the knowledge that we're going to be dealing with. So, we kind of, in many instances, we trace our understanding of physics and physical science back to the Greeks. We typically look at them as the foundation of Western, Western thinking. But I often tell folk, you have to think that the Greeks got it from somewhere, right? And so there are cultures that predate the Greeks that had strong influence on what the Greeks understood. You think about the Greeks and the Romans coexisted and worked together. There are many Middle Eastern and African societies, the Egyptian, the Moors, the Dogon of Mali, many other more ancient societies that contributed to the knowledge that the Greeks used. But the difference is that the Greeks started to move away from this this idea of superstition, if you will, and started to move into a more investigative mind approach to nature, in terms of there being some solid explanations for phenomena not based in superstition. Okay, and so they were really high on this whole investigating and experimenting as a way of understanding our nature. And then many years after the Greeks, we start to see what we call classical physics come into play, and that's built on a lot of what we study in classical physics was built through the investigations by Galileo. And you can see one of the things is that he tested things through experimentation and observation, and through that investigation he was able to uncover a lot of things that relate to motion and astronomy, two areas that we definitely focus on in this class, and that are definitely germane to physics. Okay, and then 100 years or so after Galileo, well, you can see when Galileo dies in 1642, Newton is born. So it's almost like a passing of the torch, if you will, right? And Galileo and Newton was really the scientists who formed the foundations of what we call classical physics. In fact, in this class, what you are studying is actually Newtonian physics. But remember, we're doing it from a simple perspective, right? We're not trying to get like really high in the math and the calculus, trig, and all those things. We're using some very basic baby algebra, I like to call it, and we're really high on the concepts that underlie the math, right? So Aristotle, Galileo, Newton, we're gonna see later, Kepler, but all those folk, they took knowledge and information from prior societies and generations and built on it. And that's one of the caveats of science, is that it's this growing and body of knowledge. And then after Newton, here we get into the modern era. And then folk like Einstein, they take the stuff that Newton put together and helped us to understand physics from a modern perspective, dealing with relativity and quantum mechanics, and Niels Bohr, and then you got a whole host of other folk in modern physics, Planck, Maxwell, And then we can't even, we can't talk about physics nowadays without talking about the work of Stephen Hawking, right? So, just kind of historical perspective here, right? Because, I always tell folks, this stuff isn't happening in a vacuum, right? These people were living during, you know, lived in societies that had certain values and ascribe and certain cultures and certain political climates, economic climates, all of those things, right? All right. So now what we want to focus on is we want to get a little bit deeper into this idea of physical science. And I always tell physical science to me can be summed up in a very simple way. It's scratch and sniff science, right? So it's our knowledge and our applications of knowledge that are built on measurement, observation and measurement. How do we know? Because we observed it and we measured it and we experimented on it multiple times. Does that mean that's the be all end all? No, because if somebody comes along with a better tool and they measure it and that gives a better explanation, we've got to go with that. But for now, we need to know if physical science is based on measurement, we need to understand that. How do we do it? And so we're going to go into looking at this idea of SI-based units and prefixes. In other words, the metric system. Okay. So physical quantities. That's a terminology that you'll hear me use over and over. Physical quantity or physical property. And for our purposes, that is something that can be measured, or we can use measurements to calculate it. So it's either a measurement or it's a measurement based on other measurements, right? Right. So we don't get into definitions of things like a meter, for example. I can have you memorize it or play matching with it or vocabulary test, but that's not what we're here to do, right? What we're really wanting to know is, what are these things so we can use them? Okay. All right. From an application perspective. All right. So, they give you an example here of a property that can be measured, distance and time, or two properties that can be measured. And then we can put them together to make speed. Okay. So you either measure them or you calculate them using other measurements. Okay. So I always say they're either base properties or quantities, or they're derived. And we'll see that when we start to work some examples. Okay. Now, if we're going to measure, we have to have a systematic and standardized way of doing things. Because if I say for each one of us to measure the length of the room, length and width of the room that we're in, we could all pick up a different measuring device. Okay. And so we have to have consistency, because a part of science is to have consistent communication that's easily understood and reproduced. And so we turn to utilizing units of measurement or unit systems of measurement. Okay. And so in physical science, we have some fundamental properties and some fundamental units that go along with them. And so those fundamental properties, now you see they list here, length, mass, time, and electric current. For our purposes, we don't deal with electric current in this course. So I'm going to make a quick substitution and say, for us, the fundamental properties, the fundamental quantities are length, mass, time, and temperature. Okay. And the base units that go along with them are the meter for length, the kilogram for mass, the second for time, and Kelvin for temperature. And we'll see that in the chart here momentarily. So it's not anything I need you to worry about that you have to memorize or anything like that. I'm gonna share that with you here shortly. And so you heard me mention the 4 fundamental properties: length, mass, time, temperature, and the 4 fundamental units. Sometimes you hear the word base units, base properties. The 4 base units, meter, kilogram, second, Kelvin, are from the metric system. Sometimes you hear it referred to as the SI system. SI stands for System International. System International, SI, is the name of a conference that was held in France back in the 1800s, where they came up with the metric system because they wanted to standardize things. Okay. So you have to think about what was going on back then that will require them to want a standardized way of doing things. Think about the Industrial Revolution is starting to kick off then. And so, this idea of commerce across states, across countries, across the world, we need to have a standardized way of doing things, of measuring things. And so, especially where science is concerned. And so this System International metric system came about. Okay. And so in the metric system, there are 4 fundamental properties that we care about. Properties, or you could think of another word, characteristics. There are 4 fundamental characteristics in nature that we want to measure: the length, the mass, the time, or the temperature. And if we're going to be consistent in those 4 fundamental measurements, we need base units to go with each one. And that for length, in the metric system, we use the meter. For mass in the metric system, we use the kilogram. For time in the metric system, we use the second. And for temperature in the metric system, we use Kelvin. Okay. Now we do know that in the United States, we still use the English units because of the influence of the British Empire on our country and that historical connection. We still use it, right? But we also do use the metric system to facilitate commerce and communication, especially in science. And so we're going to focus on the metric system primarily. There may be an occasion or two where I'll slip some English units in there, but for the most part, we focus on the metric system. Okay. So are there any questions at this point? I'll stop the share and ask, are there any questions? All right. So let me go ahead and get back to it. So you can see here now, that last column, you can block out that electric current and put temperature and write Kelvin, Kelvin, and the abbreviation is the capital letter K. Okay, length, mass, time, and temperature. And so think about it. You're in a class right now, physical science class, and everything we know about the stuff you're going to be studying can be explained using 4 things: length, mass, time, and temperature, and the metric units that go with it. And you might be thinking, well, okay, 4 things. we can learn those 4 things tonight and go home and we don't have to come back anymore, right? But the problem with that is that we have to be able to make combinations of these 4 fundamental properties. And as a result, those fundamental or base units, right? So if it was just 4 things, we could finish next week, we'd be done. But because we have to make combinations with those 4 things, we have to invest more time to get an understanding of what properties do we get when we make these combinations, and what are the proper units that go with them, and then how do we use it, okay? So I apologize for the small print here, but we'll be looking at a source here in just a few that, you know, visually is a bit more appealing. And what they're showing here are the metric prefixes, okay? Now, and they give you a large table of them that they say are commonly used in physics. That is true, but we won't be using all of these, okay? And let me just say this right now, even if we were, I would never expect you to memorize them. I would expect you to take this chart out and use it anytime you want. So the question then is, what are these metric prefixes useful for? Well, remember I said we're going to be measuring things. And every time we measure something, we aren't going to get 1 meter, 1 kilogram, 1 second, 1 Kelvin. We're going to measure, and sometimes we'll get more than 1, and sometimes we'll get less than 1. So these metric prefixes allow us to make multiples of our base or fractions of our base. And we make those multiples or fractions using powers of 10, okay? And so every metric prefix meaning it comes before the base, every metric prefix has an associated power of 10 and an abbreviation, okay? And so your task is to utilize these metric prefixes and their associated power of 10 and abbreviation to help you express measurements as multiples of or fractions of a base, okay? So like kilograms, kilo meaning 10 to the 3 or 1,000. So if you have a kilogram, you have 1,000 grams. If you have a mega meter, you can see on the sheet there, mega is 10 to the 6 or a million. So a mega meter means you have 1,000,000 meters, okay? A centigram or a centigram, or let me use a different base there, a millisecond, okay? So milli means 10 to the minus 3 or 1,000. So a millisecond is 1,000 of a second, okay? So multiples of or fractions of our base. And again, I don't need you memorizing any of it. I need you to pull out the chart and use it when you have to, okay? And you won't be using all of these. There'll be a fairly standard set, you know, kilo, milli, nano, micro, centi, fairly standard smaller subset that you'll be using more frequently because of the types of things that we measure in this course, okay? Or the types of measurements that we utilize in this course, okay? Now, this starts to go into unit conversions. I'm not going to go into unit conversions or the rest of this packet in here using this packet. I'm going to utilize another source to talk about unit conversions. So what I want to do for right now is I want to stop the share and ask if there's any questions on this stuff before I jump into unit conversions. Okay. All right. So here's what we're gonna do. Stop the share. I'm gonna say, let's take a 10-minute break. I'll stop the video. I'll turn my mic off. If you think of something while we're on break, when we come back, we'll take a few minutes. We'll answer any questions, and then we'll move on. We'll start to look at some combinations of these properties as well as unit conversions. 10 minutes. It's 7 o'clock now. Let's get back together at 7:10. All right, everybody. Thanks for coming back. We'll go ahead and pick up where we left off. So let me share my screen. All right, so in the remainder of the time that we're together tonight, I'm gonna focus on two things. So I wanna focus on this notion of derived properties, right? Because I said that we can take our base properties and make combinations, and then we have to make appropriate combinations of the units. And the other thing I want to focus on is unit conversions, okay? Now, I'm going to do that by using the extra resources that I mentioned to you that I would come back to. So in the announcements, you can see you have access to a whole host of things in the announcements right now. But the one I'm going to focus on says extra resources, okay? And if you click on that link, and then the link that's there too, inside the extra resources, it'll take you to some of my shared space on Google Drive. You don't need anything special to utilize this. I've enabled it so that anybody with the link can use it, okay? So what you'll notice is that there's a folder for every topic that we cover in this course. So there's some extra resources for every topic that we cover. And a lot of times when I want to show you example problems, I'll do it utilizing these extra resources, okay? So I'm going to go into the one that says measurement, because that's what we're focusing on now. Just let me just go back one. I apologize. Yeah, so measurement. That's what I wanted to make sure of. Okay, so there it is right there. So there, see, there's some extra notes on the nature of science if you want to go take a look at them. There's some extra notes on just on measurement and science in general. Okay, but I'm going to go into the extra notes and I'm going to look at the part on units and unit conversions. Okay, so you can utilize these however you like, whenever you like, but sometimes I will refer to them to do some problem solving, because I think these examples that are in this packet really show the kinds of things that I would expect you to be able to do. Okay. All right. So as I mentioned, that this idea of measurement is important. And anytime we measure any quantity or any property, we always get a number and a unit. So you cannot correctly specify any measurement without giving the correct number and the correct unit, okay? And my motto and the way I operate in this class is your number can be spot on, but if your unit is correct, it's wrong, okay? If your unit is wrong, it's wrong, okay? Units matter, okay? All right. And then here is a much smaller chart showing, well, no, this is a chart showing the base quantities or base properties, length, mass, time, temperature. Remember, we don't do current. And then the base unit, meter, kilogram, second, Kelvin, and the abbreviation. Okay, same information that I covered in the other packet that I utilized. But the nice thing I like here is that this is a chart of the metric prefixes, the abbreviations, and their power of 10. And this is useful because it's a much smaller subset of the larger chart that I showed, and it is more reflective of the prefixes that we'll be utilizing, okay? Again, you still don't have to memorize this. You can always have this available and utilize it anytime you need to, okay? Anytime, all right? And so I want to focus on this idea of derived units now, okay? So I said that we can make combinations. Remember, we make combinations of our base properties and get a new property. And then we make combinations of our units to get the appropriate unit to describe that property, okay? So an example of a derived property is volume, okay? Volume is an example of a derived property. How do we get that volume? How do we get that derived property volume? So we take a length times a length times a length. You might, in math class, say length times width times height. Or you might have heard volume expressed that way. Length times width times height. Well, if you think about it, width is a length. It just tells you how wide. Height is a length. It just tells you how high. So at a fundamental base level, what you're doing is doing length times length times length in order to get volume. Length is a base property. And when you multiply it 3 times, you get a derived property volume, okay? So I'm gonna see if you're thinking, if I were to say I want a derived property that looks at length times length, anybody know what that derived property is? Just to see if you're absorbing the concept. Length times length. What is that derived property? You can type it in the chat if you know. So I'll give you a hint. So instead of having cubed units like you get for volume, you'd have square units, like square feet, square inches, centimeters squared. Any idea what property that is? Okay, so it's a property that we use quite commonly. For example, if you're going to put carpet in your house, you want to know how many square feet or square yards you might need, and that's area, right? Area, okay? So that's the idea of making combinations. So we focused on volume here because volume is part of another very important derived property that we'll look at in just a moment, okay? But when you combine length times length times length, you get units for volume like centimeters cubed. Centimeters cubed is an example of a length volume. And the way you got that length volume is multiplying length times length times length. And so you have to take the unit centimeter. Centimeter is a length unit. And you multiply centimeters times centimeters times centimeters, and you get centimeters cubed. Or you could take decimeter. Decimeter is a unit of length. And you multiply decimeter times decimeter times decimeter, you get decimeter cubed. Inches is an English unit of length. And if you multiply inches times inches times inches, you get inches cubed. Or feet times feet times feet. You get feet cubed. The idea is that you have to take a length unit and multiply it times itself 3 times to get a volume unit because it has to be cubed, right? So if you took miles, miles times miles times miles, miles cubed, or kilometer. Some folks say kilometer, right? Kilometer times kilometer times kilometer. Kilometers cubed. That's a volume unit, a length volume. But you can also have liquid volume, right? Like if you took your bottle of soda or can of soda and you looked at it, the label, you might see units like milliliters. That's a volume unit. Or You might see liters. If it's a big enough item, it might be in liters or gallons. We typically measure, think of milk, go get a gallon of milk, right? Gallon is a volume unit. Or if you look at like baby formula, you look at the can, you'll see fluid ounces. Fluid ounces is volume, right? Because that's liquid, okay? Those of you in my lab class will have the opportunity to utilize some of these volume units, because you'll be doing an experiment that has data dealing with volume, okay? In particular, liquid volume and the relationship between liquid volume and length volume. So you see given here on this slide, 1 centimeter cube equals 1 milliliter. So think of a cube. And if that cube had a length of 1 centimeter, a width of 1 centimeter, and a height of 1 centimeter, you'd have a volume of 1 centimeter cube. And if you fill that cube with liquid, it would have a volume of 1 milliliter. Okay, so there's an equivalence between liquid volume in milliliters and length volume centimeters cubed. Or you see, for example, 1 decimeter cube, which is length volume, equals 1 liter, which is liquid volume, okay? So that, those are all different and valid units to measure volume, okay? So the property is volume, and you have many different units. But if I pick a unit, for example, if I say gallons, that doesn't measure length, that doesn't measure time, that doesn't measure mass, that doesn't measure temperature. Gallons can only go with one property, and that's volume. So a property can have many different units, but a unit can only go with one property, okay? So that's a very important concept to understand in measurement. A property can have many different units, but a unit can only specify one property, okay? All right, so let's take a look at another derived property called density, okay? Density is a derived property. How do you get this derived property? Well, you take mass, which is a fundamental property, right, a base property, and you divide it by volume, which is a derived property. So now we've gone from making just combinations of our base property to making combinations of combinations, right? And that's why I said that's the challenge, right? To all these different combinations that we can make, okay? So to get density, you have to take a mass and divide it by a volume. And they give an example of units, grams per centimeter cube. How do we get that? Well, the gram is an example of a mass unit, and the and a centimeter cube is an example of a volume unit. So a mass unit divided by a volume unit will give you density units, okay? All right, so what I'm gonna do now is I'm gonna open up a whiteboard. I like to use this one here, and I'll share this with you afterwards. When I make the, when I post a video from tonight, I will include in it this screen here. I'll save it for you. So we have a property called density, and the way we get that density is to take mass and divide by volume. This is the equation. When we write an equation, we don't write it in words form, we write it in symbol form. So the symbol form of density is mass over volume. You're seeing this whiteboard right now? I can't, well, let me stop the share because I'm not sure if anybody could unmute, but were you seeing, somebody just type in the chat for me, were you seeing that screen? and then I'll go back and share it. Thank you. Okay, so I'll go back and share that now. So density equals mass over volume. So this is the density formula. Okay, and so let's spend a moment with that. So for example, there are a lot of different units that I can use for mass. Okay, there are a lot of different units that I can use for mass. I could use grams. Okay, I could use ounces. I could take, you know, my metric prefixes, and I can make a centigram, a kilogram, or any other prefix that I want to put on it, right? The prefixes go with our metric base in the unit, in this case, grams, right? Centigrams, kilograms, you know, megagrams, right? Okay. We just saw that there are lots of different units for volume. So we had what? Centimeters cubed. We had liters. We had milliliters, gallons, all kinds of nice volume units, fluid ounces. Okay, these are all volume units. And now, how do we get our density units? We can take any one of these divided by any one of these, for example. Okay, now there are many others, right? But I'm just giving some examples to highlight the concept, right? So now, how do we get our density unit? Well, pick one from the top row and one from the bottom, right? So we could have grams per milliliter, right? I could have ounces per fluid ounce. Okay. I could have kilograms per liter. I could have kilograms per gallon. I could take any mass unit and divide by any volume unit and get a density unit. Okay, so that's the idea. Mass is a base property, volume is a derived property, and when I combine these two, I get another property called density. All right, now you see on the screen this little triangle with the smiley faces. Yeah, I'm really happy about the smiley faces, but it didn't really copy what I wanted. So let me show you. This is called my problem solving pyramid. Okay, my problem solving pyramid. And this is how we do algebra in this course. Okay, I try as much as possible to utilize the pyramid when we're doing algebra, simple algebra, so that you don't have to even know how to do equations. All you have to do is understand multiply or divide. If the two variables are on top of each other, you're dividing. If they're next to each other, you multiply. So for example, if I wanted to find volume, I would just cover up the V and say, to get V, I take M divided by D. If I wanted D, I would cover it up and say, to get D, I take M divided by V. If I want M, I cover it up and I say D times V, because they're next to each other. So using the pyramid allows me to do the math without having to really you know how to solve equations. Okay, if you know how to solve equations, great. But if you don't, you can always use the pyramid. And the nice thing about the pyramid is if you fill in the things that you know to get the thing that you're looking for, that'll be the thing that's left. Okay, and then you just multiply or divide. Okay, so that's an example of a derived property, density, and the pyramid that you can use to go along with it. All right, so in this packet, I like because there are examples that utilize the pyramid. And so you're going to have to do some density calculations in your problem set, and you can come back to this packet as an example of how you solve density problems, okay? So it says an object has a volume of 825 centimeters cubed and a density of 13.6 grams per centimeter cubed. Find its mass, okay? So they want you to find M. So to find M, you have to do D times V, right? So on the work that's being shown here, they're multiplying D times V. 13.6 grams per centimeter cube times 825 centimeters cubed, okay? When you use your calculator to multiply, you get 11,220. And the centimeters cubed cancel, and you're left with grams. Now, when you problem solve for me, you know, you could be multiplying and have a number that has 9 decimal places. 2 decimal places is more than sufficient. I'm not going into significant figures and precision. I figure we got enough on our plate just to manage, you know, the math that we do have to do. And so always you can round off to 2 decimal places for me, and that's sufficient. All right. Any questions here? If you can unmute, feel free, because I can't see the chat while I'm sharing the screen. Okay. If you can't unmute, then just give me a few, and then I'll give you a chance to ask your question. All right, let's look at another example using the density formula or the density pyramid. It says a liquid has a density of 0.87 grams per milliliter. What volume is occupied by 25 grams of the liquid? Okay, so they want us to find volume. They ask what volume? Okay, so cover up the V. And now we know if we want to get V, we have to take M divided by D. So that's 25 grams divided by 0.87 grams per milliliter. When you do that, 25 divided by 0.87, 28.7. The grams cancel out because I can see it clearly. I have grams on the top and the bottom, so they cancel, and I'm left with milliliters, okay? And so this is the kind of thing that you will have to do on the problem set. So you can come directly back to this and see, if I'm solving for V, how do I do it? And you can use this as a guide. And then the last one, you have a sample with a mass of 620 grams and a volume of 753 centimeters cubed. Find the density. Well, if I want D, what do? I cover up D with the smiley face there, and then it tells me I have to do what? M divided by V. So do that. M divided by V, 620 grams divided by 753 centimeters cubed. The number part comes out to be 0.82, and nothing cancels here as far as the unit goes, so I'm left with grams per centimeter cubed, right? So those are 3 examples. In each example, I found one of the variables in the density formula, density pyramid, so that you have an example of how you find each one of them when you're doing the problem set, okay? So I'm stopping the share. If you have a question, you can either unmute and ask it, or you can type it in the chat, and we'll take a few moments and answer any questions you have regarding derived properties or derived units. All right. So from what I'm seeing, it looks like there aren't any questions. Oh, wait, let me see. Let me stop. I apologize. Let me say it. The 3 on centimeters doesn't mean anything. Yes, it means cube. Cubed means you multiply it times itself 3 times. Centimeter by itself is length. Centimeter cubed with the 3 on it is volume. 2 different properties. Does that answer your question, Damien? I would take it beyond just a definition, because if you're solving for volume and you write centimeters, that's the wrong property. So it's beyond the definition, is being able to use these units effectively to communicate a measurement, which is meant to explain some portion of your physical environment, right? So if I ask you for length and you tell me centimeters cubed, you're talking about volume and I'm talking about length. So we have to be using these things correctly to correctly communicate the measurements that we're making. And remember, everything we do in physical science is based on measurement. So if you're telling me the wrong unit, then you're describing my physical environment incorrectly. Okay, does that make more sense to you? No worries, I get it completely. Yeah, that's why I would not skip over this, because I recognize that you know, that's a reality for a lot of students. So you don't, yeah, you don't need to feel like you know, that, you know, that's a problem of any kind. That's absolutely expected, and I appreciate you being you know, brave enough to ask your question, because I always tell some, you're not just asking the question for yourself, you're saving your classmates. So consider yourself a really brave hero for putting that out there, because these are the kinds of simple things that if you don't ask can cause you grief down the road, right? We want to make sure everybody's catching on to this. So I really do appreciate you asking the question. All right. So let me go ahead and share my screen. And now that we've looked at the notion of derived properties, and more importantly, we've spent some time getting acquainted with the idea of the metric system and prefixes and units, we can now start to talk about measurement conversions. Okay. All right. So inevitably, if we make measurements, we could be using different units. You know, our cousins overseas in England will be using the metric system, and we grew up in the United States, so we will be using English systems, right? Units, right? And so if we want to be on the same page, either I've got to take my English units and convert them to metric, or they've got to take their metric units and convert them to English for us to both be speaking the same language. So this idea of unit conversions is simply so that we can have equivalent communication and equivalent measurements, okay? We're taking one measurement and converting it to an equivalent measurement using a different unit, all right? So for example, I could say 12 inches, or I could say a foot, or I could say 3.28 meters. All of those are equivalent. But if I'm talking to my counterparts in Germany, I will be using meters, 3.28 meters, because they don't use feet and inches. Okay, so remember, all of this is for consistency and communication. All right. So in this packet, there are two methods for unit conversion that are covered. Feel free at your own convenience to look at the SI prefix conversion method. I'm not going to focus on that because I utilize the dimensional analysis technique, and that is because I can do metric conversions. The SI prefix conversion method is for doing metric conversions, metric to metric. Well, if I'm using the dimensional analysis, I can do metric to metric. But if I use the dimensional analysis, I can do English to metric, metric to English, English to English, or metric to metric. So the dimensional analysis technique is much broader. It allows me to do more things. In fact, with the dimensional analysis technique, I can do any conversion. So I'm not going to focus just on the SI prefix conversion method because I can only do metric conversions with that. If I'm going to learn how to do unit conversions, then I might as well focus on a technique that allows me to do any type of unit conversion. Okay, so that's the kind of method to my madness here, if you will. Okay, all right, so I'll skip over all of that. It's some great stuff, and you can go take a look at them, but I'm going to focus on this technique. It's called the dimensional analysis technique. And it is based on one major idea, and that is you can cancel units just like you cancel variables, or just like you cancel like variables, okay? So that's what they're showing you there, all right? So centimeters cubed cancel centimeters cubed because they are like, all right? So here is a set of steps that explain the dimensional analysis technique. But let me put the brakes on real quick and say this. If you are comfortable doing unit conversions and you have your own way of doing it, do it. You do not have to use my technique. But here's what you do have to do. No matter what technique you use, you have to show me. This class is not about just getting the correct answer. This class is about how you got the answer. Showing me how you got your answer is just as important as having the correct answer. In fact, if your answer is correct and you don't show me how you get it, I will mark it wrong. This is about show me. So when you do unit conversions for me, you can use any technique that you want, yours, mine, or somebody else's, but you must show me, okay? So what I'm sharing with you now is a way to do unit conversions if you don't have a way or don't know a way, or maybe you do know a way, but it's been a minute since you've done them, so you want to get yourself back in the groove, okay? So let's talk about the steps that you have to follow. even if you're doing them fast, like subconsciously, you're still doing these things when you do a unit conversion. Okay, so when you're going to do a unit conversion, it's very important to know what unit are you starting off with, meaning what unit do you already have, and what unit do you want to end up with. Okay, so when you finish, what unit should you be getting or do you want to get? Okay, and then you're going to line up a conversion factor so that the units cancel. Okay, so now we've got to get into this whole business of what is a conversion factor, and then what do we mean by line it up? Okay, so we'll see that in just a moment. And then once you've done that, you multiply all your top numbers and divide by all the bottom numbers. And we'll look at that as well. Okay. And then of course, I always tell students, no matter how good you are or how good you think you are, it always helps to go back and check your math and also make sure that you're getting the unit that you in fact should be getting or want to get. So let's talk about this conversion factor. So a conversion factor is nothing but a fancy way of writing 1. And you learned very early in your math life that if you multiply or divide by 1, you don't change the value. So the nice thing about a conversion factor is I'm multiplying by 1, so I'm not changing the value. I'm just writing it in an equivalent form. Okay. All right. So a conversion factor is nothing but a fancy way of writing 1. Well, the next question is, where do you find these conversion factors? If they're fancy ways of writing 1, where do I get them? Well, you have some options. Many times conversion factors are written in the front or back cover of a textbook. Your textbook, if you go into the weekly overviews and there are some resources. If one of them has a conversion chart in it, right? But inevitably, a conversion chart that's written in a book or on paper is limited, right? Because you can't write every unit conversion there. I have also bookmarked for you under useful links on the left menu, conversion tool. So you can use this, see, because there are conversion factors there. Okay, so for example, if you wanted a weight mass conversion, let's say I wanted to, 5 kilograms, and I want to know how many megagrams that is. Megagram, sorry. Okay, so you can see here, it did the conversion for you. Okay, you can utilize that as well. My only restriction on a unit conversion tool is you won't have access to it on an exam. So you need to have something with some, some fairly basic unit conversions. Maybe you want to take a photo of the front or back cover of a textbook that has conversion factors, or you want to, have on a sheet of paper some basic ones that you might want to have access to during an exam. But you won't be able to get online and go to extra websites during an exam, is what I'm trying to get across to you, right? But when you're doing problem sets or homeworks or discussions, feel free, okay? So, in the weekly overviews, let me just see if I can quickly come up on the one that that I made available to you. Supplemental notes, I believe it is. Yeah, there we go. So you see, got a conversion chart there, that kind of thing. Okay. All right. So feel free. All right. But what we want to look at now, again, so a conversion factor is a fancy way of writing 1. You can find conversion factors in charts and tables in the front or back of textbooks, online. The question is, once you have them, what do you do with them, right? So one conversion factor that you'll regularly come across is 1 inch is equal to 2.54 centimeters. 1 inch is equal to 2.54 centimeters, right? So let me just write it here for you. 1 inch is equal to 2.54 centimeters. And I'm giving you this as a conversion factor. I do believe your textbook says 1 inch equals 2.2 centimeters. They're a bit too far off for my taste. I wouldn't penalize you if you use that, if you used it because it came right out of the textbook, but they're off. 1 inch is 2.54 centimeters. Okay, so that's a conversion factor right there. Okay, the question is, if I gave you 1 inch equals 2.54 centimeters, would you know how to line it up properly? So let's take a look at that. So you can see here that on the first one, it says 1 inch, and then it's divided by 2.54 centimeters equals 1. Yeah, it equals 1 because they're equal to each other, right? And if you divide by something that's equal, you get 1. 1 inch divided by 1 inch is 1. 1 inch divided by 2.54 centimeters is 1 because they're equal to each other. Okay, but notice how they're lined up here with the inches on the top and the centimeters on the bottom. If they're lined up like that, then it means I am trying to cancel out my centimeters and keep inches. In other words, I'm trying to convert my centimeters into inches. Okay, if it's lined up like that. Well, take a look at how it's arranged on the bottom. 1 inch, but this time the 2.54 centimeters is in the numerator and the 1 inches is in the denominator. They're still equal. They're still being divided by each other and equaling 1 because they're equivalent to each other. But look how they're lined up this time. The way this is lined up, it means I'm trying to convert my inches to centimeters. In the top one, I'm converting my centimeters to inches. In the bottom one, it's lined up so that I'm converting my inches to centimeters. Okay? Right? The top one, I'm going from centimeters to inches. The bottom one, I'm going from inches to centimeters. Okay? All right. So let's look at some examples of utilizing this dimensional analysis technique. Some actual conversions. And you can come back and look at these conversions as examples to follow when you're doing problem set number 2. Problem set number 2 deals with unit conversions. Okay. I don't think problem set number 2 is due Saturday. I think problem set number 2 is due next Saturday. So you will have some time to practice this, right? So let's look at a couple of examples here. It says your European hairdresser wants to cut your hair 8 centimeters shorter. I don't know. Fabio got in the hair business. I have no idea. But, if I was in Europe and they said, I want to cut your hair 8 centimeters shorter, I would be like, hold up, because I don't think centimeters, I think inches because I grew up in the United States. I would have to say, give me a minute. I need to do a quick unit conversion before you cut my hair, right? So I'm starting off with 8 centimeters. That's the measurement I have. I want to take that measurement and convert it to an equivalent measurement in inches. How am I going to do that? I'm going to take my conversion factor, 1 inch is equal to 2.54 centimeters, and line it up, see, line it up so that I cancel out the centimeters. Okay, in order for the centimeters to cancel, that part of the conversion factor has to be on the bottom or the denominator of my conversion factor, okay? So this is the measurement that I have. This part is my conversion factor, and I'm going to cancel out my centimeters and then multiply and or divide. 8 times 1 divided by 2.54, 3.15 inches. So 8 centimeters is equivalent to 3.15 inches. So if you're in Europe on holiday and Fabio tells you he wants to cut 8 centimeters of your hair, okay, Fabio, that's 3.15 inches. I don't know. I don't have enough hair for him to cut 3.15 inches. Maybe you do, okay? All right. Any questions here? If you have a question, type it in the chat. And as soon as I'm done, I'm going to come back and I'm going to answer any questions that are there. Here's another example. How many milliliters are in 1 quart of milk? So I have a quart of milk. And I don't know, for whatever reason, I want to know how many milliliters is that? Okay. So notice what's going on here. I started out with a quart. I want to end up with a milliliter. But they didn't convert directly from quarts to milliliters. If you notice here, the way they have these conversion factors lined up, they first converted to liters, and then they converted the liters to milliliters, okay? So in the middle here, there's an intermediate step. And I'm using the conversion factor, 1 liter equals 1.057 quarts. 1 liter equals 1.057 quarts. And I line that conversion factor up so that the quarts is in the denominator. So I'm canceling out my quarts. When I finish that first step, I won't have quarts anymore. I will have liters. And then in the second step, I'm going to convert those liters into milliliters. Okay. Now, again, you would get these conversion factors from a conversion chart. And then you multiply all your top numbers, multiply all your bottom numbers, then divide. So 1,000 divided by 1.057. That gives you 946 milliliters. Could you break this down into 2 steps? And first, convert your quarts to liters. And in the second step, convert your liters to milliliters? Absolutely. They lined it all up in together, but you could break it down into 2 separate conversions. In the first step, convert your quarts to liters. The second step, convert your liters to milliliters. All right. So you might have the question, why didn't they just go directly from quarts to milliliters? Well, maybe the conversion chart that they have doesn't have a conversion factor that goes directly from quarts to milliliters. The conversion chart that they're using only has a conversion factor that goes from between quarts and liters. That makes sense because a quart is almost the same size as a liter. So it's a logical conversion factor to have. And then the second conversion where you're doing 1,000 milliliters in a liter, well, milli means 1,000. And so in order to have 1, you have to have 1,000 of them. So 1,000 milliliters equal a liter, okay? All right. So again, once you line up your conversion factors, make sure they're correct. Make sure that you can properly cancel units that you want to get rid of and end up with the unit that you want to have. All right. look at another example. It says, assume your mass is 55 kilograms. How many pounds do you weigh? Okay, so we're starting off with 55 kilograms, and we want to know what's the equivalent in pounds. So I pull out my conversion chart, and it tells me that 2.2 pounds is equal to 1 kilogram. So I'm looking in the front cover of my textbook, for example, and I see 2.2 pounds is equal to 1 kilogram. So now I got to take that conversion factor and line it up so that I cancel my kilograms. Why do I want to cancel the kilograms? Because they ask me how many pounds is this. So I need to cancel out the kilograms and get an equivalent measurement in pounds. So I line up my conversion factor so that I cancel my kilograms, and then 55 times 2.2 is 121 pounds. I don't have kilograms anymore because I canceled them out. I'm left with pounds. Okay. So that's another example of utilizing a conversion factor to do the dimensional analysis type unit conversion. And if you look at the examples that I've worked so far, you can see I have metric conversions, I have English conversions, conversions between the two. So it's, it's a very powerful technique. All you need is a conversion factor. 6. Well, it says number 6 in this packet, but how many feet long is a 5K, 5-kilometer race? So, a lot of times you see marathons, they talk about 5K or, 10K or what have you. The question that we're being asked here is to find the equivalent in feet. So a 5-kilometer race, how many feet is that? All right. So pull up my conversion chart. The first conversion I see, 1 mile is 1.609 kilometers. 1 mile is equal to 1.609 kilometers. That's a fairly standard conversion factor that you'll find in many textbooks because a mile and a kilometer are fairly, evenly matched, right? It's a logical conversion because they're almost the same size. Okay, so I've got to take that conversion factor, 1 mile equal to 1.609 kilometers, and I've got to line it up so that I get rid of the kilometers. I can't keep the kilometers because they ask me for feet. So I've got every conversion that I make has to bring me closer to feet. I don't have a conversion that goes directly from kilometers to feet. The only thing I have going for me is I can convert my kilometers to miles, and then I can convert my miles to feet. All right. So in the first step, I'm going to line up my conversion factor, get rid of the kilometers. And then in the second step, I'm going to line up my conversion factor, 5,280 feet per mile. I'm going to line that up so that I get rid of the miles. Cancel out the miles. Okay. So now, once I've canceled out my kilometers, I've canceled out my miles, then I can multiply 5 times 5,280 and divide by 1.609. And that gives roughly 16,408 feet. Now, if you're doing it and you get a decimal number, no problem, 2 decimal places and you're good. Okay. So if you run a 5-kilometer race, you run the equivalent of 16,408 feet, right about. All right. Again, if you're following along and you have questions, make a note of it. Once I stop the share, I'll address your questions because I can't see the chat or you while I'm sharing the screen. How many grams does a 10-pound bag of potatoes weigh? So, you know, what is it? Labor Day is coming up here in a few days. Gonna break out the barbecue. Hopefully the weather holds up and make you some potato salad. And you go to the store and you buy you a 10-pound bag of potatoes. And somewhere in the back of your mind, you're thinking metric. What's the equivalent in metric? How many grams is that? Okay. So let's take that 10 pounds and convert it to grams. Now we already have a conversion factor, 2.2 pounds per kilogram, right? But notice this time how I have to line it up. In the example that we worked before, I was converting my kilograms to pounds. This time I'm converting my pounds to kilograms. So that's why the pounds is on the bottom, because I have to cancel out that unit. Okay. So every 1 kilogram is equal to 2.2 pounds. But since I'm going to cancel out my pounds, I have to line up the conversion factor so that it's in the denominator. So after the first step, I will no longer have pounds. I will have kilograms. And then I have to take those kilograms and convert them to grams. And there's 1,000 grams for every kilogram. Kilo means 1,000. So if I have 1,000, if I have 1 kilogram, I have the equivalent of 1,000 grams. But I'm gonna line that up so I cancel out my kilograms. So I no longer have pounds. I no longer have kilograms. I'm left with grams. 10 times 1,000 divided by 2.2, 4,545 grams. So that 10-pound bag of potatoes that you buy at the grocery store is the equivalent of 4,545 grams. Okay. And then the last question here, take us into football season. And I changed the names on the teams because I didn't want to offend any fans out there. So it says tag football needs 550 centimeters for a first down. How many yards is this? Well, hold on. I don't know where Taft is playing, but in the United States, we don't measure football in centimeters. So if they need 550 centimeters for a first down, I need to hurry up and do a conversion to yards because I need to know how far does my quarterback have to get us down the field, right? So let's see how many yards that is. I'm starting with a measurement of 550 centimeters. And I don't have a conversion factor that goes straight from centimeters to yards. The conversion chart that I'm using only has 1 inch equals 2.54 centimeters. And then 1 foot is equal to 12 inches and 1 yard is equal to 3 feet. Okay. So I got to figure out, I got to take those 3 conversion factors and line them up just right so that I ultimately end up with yards. So the first thing I'm going to do is I'm going to get rid of those centimeters, period, and convert everything to inches. Once I have it in inches, then I can start to work my way into yards, right? Because in this country, I don't do centimeters. We do, we do inches, feet, yards, miles, so on and so forth, right? So let's take the first step, line up this conversion factor. 1 inch equals 2.54 centimeters. Let's get rid of those centimeters. And now we're left with inches after the first step. The next thing I need to do is take those inches and convert it to feet. Because remember, I don't have a conversion factor that goes straight from inches to yards, but I do have a conversion factor that'll take me from inches to feet. 1 foot is 12 inches. So I line that up so I cancel out my inches. But I'm not done yet. Because after the second step, I have feet. They didn't ask me for feet. They asked me for yards. So I've got to take one more step and convert those feet into yards. So there's 1 yard for every 3 feet. Line that up so you cancel the feet. If I line it up correctly, the feet should be in the denominator because that's the unit I'm trying to get rid of. Okay. So now look at, I got rid of my centimeters. I got rid of my inches. I got rid of my feet. When I finish, I'm going to have an answer that has a unit yards because that's the unit that's left. That's the unit I want. So 550 centimeters on the top, and then I have to do what? 2.54 times 12 times 3 in the bottom. So this time, be careful here, because if you're not careful with how you group things in a calculator, you multiply and divide incorrectly. So my rule is always, I multiply all my top numbers, I multiply all my bottom numbers, and then I divide. So that way I'm sure I don't make a mistake. So yeah, 550 times 1 times 1 times 1. Got 550 in the top. 2.54 times 12 times 3. And then I get a number for the bottom. And then I divide those. Okay. Multiply all your top numbers, multiply all your bottom numbers, and then you divide. And so you'll be left with 6.01 yards. Now 6 I can get with. How are they going to measure 0.01? That's debatable, right? So there you go. We're ready to kick off football season. All right. So again, this packet has multiple examples that you can come back and refer to. So right now I'm going to stop the share. And any questions that you have, let's take the last few minutes that we have and get those answered. I can definitely respect that, Damien. You're soaking it all in. But here's what I need you to, I need all of you to make a commitment to me that while you're working this weekend on whatever you're working on, no matter what it is, how big or small, if you have a question, I need you to reach out to me by email or come and see me during office hours that I have for the rest of this week so that I can get your question answered so that you get off on the right foot, because this preliminary information, it might be a review for some of you. It might be the first time some of you are encountering it. Might be that you've seen it before, but it's been a while. No matter where you're at in your in your progression, no matter what your question is, you've got to commit to me that you're gonna find a way to reach out to me and get that question answered. If you can do that for me, and you don't have any questions right now, we're done. You do the same, Michael. Thank you for sticking it out with me today. No problem, Damien. Have a great weekend. Savannah, you do the same thing. Have a great weekend. Well, good rest of your week and a great weekend. All right. If there are no questions, I'm going to stop the recording.